All right, welcome everyone to this week Autonomy Talks. This week is a pleasure to have Professor Negar Mehr with us. Something about her. So Negar Mehr is an assistant professor at the University of Illinois at Urbana-Champaign in the Aerospace Engineering Department. She received her bachelor and her bachelor, in mechanical engineering from Sharif University of Technology in Tehran. And then she moved to US, where she got her PhD in mechanical engineering at UC Berkeley in 2019. She then moved to Stanford University, where she worked on her postdoctoral fellowship, and she then joined University of Illinois. Her research interests lie in the intersection of control theory, robotics, and game theory. And in particular, she's interested in developing control algorithms which enable robots to safely and intelligently interact with other agents and humans. Notably, her work has been awarded the Best PhD Dissertation Award from the ITSS, and she also won a Best Student Paper Award at the International Conference on Intelligent Transportation Systems. Today, she's going to talk about probably some recent developments in this area and some vision for the future, and we are very happy to hear what she's going to talk about. So Negar, go ahead, the stage is yours.
Hey, thanks a lot for the kind introduction. Hello, everyone. I'm Negar, and I am excited to share some of the recent work that we've been thinking about and doing in my lab, ICON Lab, Intelligent Control Lab, about developing planning and control algorithms to enable socially aware autonomous systems. I think for people like me who are working in controls area, this is particularly an exciting time because there are so many opportunities and ways that we can think of autonomous systems transforming our lives. We've been hearing about autonomous cars for a couple of years, and we're hoping that we will have autonomous cars on roads at a larger scale pretty soon. Factory robots in warehouses, robots delivering foods, manipulators in sort of collaborating with each other on difficult manipulation tasks, or drones delivering packages in the world. And this was actually something we saw during the COVID pandemic a lot, that drones delivered some medical aids and were used for disinfecting areas. So there are many opportunities for robots to enter our lives. But one sort of aspect that is common among all these tasks is that in all these tasks, robots must intelligently interact with either other robots or with humans in the environment. So there are some intelligent agents in the environment that robots must interact with in order to succeed in these type of tasks. And this is a particularly challenging task for robotic systems because if you think about it, traditionally robots were deployed and developed for very structured environments. We even had cages around the robots to just make sure that there wouldn't be much of an interaction between the robot and other agents. But these type of new applications happen in a very unstructured environment when robots have to interact with other agents. And unfortunately, the robots are not still good at those type of interactions. Just this past July in Ocado, which is a UK-based online grocery store, because of the collision that happened between 3 robots in the company's warehouse, there was a fire, and basically many of the orders were canceled, and the company's share price dropped by 6% just because of 3 robots colliding with each other. That was actually very interesting to me because such collisions happened in a even a structured environment like a factory space where there is this grid structure out there, and I'm assuming there is a lot of assumptions and restrictions that have been added to the system to make it more structured. But the fact that these type of collisions are happening in such an environment make it no surprise that out in the world, when robots interacting with humans, things can become even more complicated. I think many of you may have probably seen this video that the Waymo car is trying to merge onto the freeway, but because it cannot interact with human-driven cars on the road and merge to the freeway, cut in front of them to change lane, it remains on the exit lane and it has to exit the freeway. So basically, it cannot figure out how to merge onto the freeway and how to interact with other cars on the road. And if you want to think about it, what is the challenge? What is it that makes planning and decision-making in such interactive settings challenging? Is that in order for robots to succeed in these type of tasks, we need the robots to be social in the sense that they need to account for the dependence of all agents' decisions upon one another. We really need the robots to know that their action that they take would affect the sort of cost measure that the other robot or the other human-driven car would experience on the road, and the robots need to account for that. But how should we mathematically think about the accounting for this coupling between agents' decisions? Traditionally, when we had one agent, we can think of accomplishing or succeeding a task as a planning problem in the sense of an optimal control problem, where we say every robot should take actions that minimizes, let's say, its cost or maximizes its utility if we are using the language of a reward function. So in the single agent setting, we could just simply say the robot minimizes its cost measure. But let's say there is another robot in the environment, and that second robot has its own objective function. Then we cannot simply say that let the second robot also minimize its cost, because J1 and J2 will be dependent on what action or what state the other robot may have. For instance, if there is a term in the cost function that penalizes for the collisions between the two agents, the fact that the other agent is there would affect the performance measure or the cost function that each of those robots would see. So it may not be possible to say both of them just minimize their cost functions because they are coupled. And then you can even think about it that things become more complicated when there are some agents such as humans in the environment where basically you cannot directly control them. So the question is, moving from this notion of optimality in the single agent setting to some form or some extension of optimality in the multi-agent setting, how should we think about the outcome of interaction between these agents? How can we mathematically quantify that? And this actually has been something that has been studied in the game theory literature for a long time, that if sort of strategic decision makers are interacting with each other, how should we model the outcome of interaction? And it has been shown that the extension of this notion of optimality to the multi-agent setting is indeed this notion of equilibrium in games. Where at equilibrium, what we say is that if we let's say we let the policy of agents at equilibrium be UI star for every agent I, and then for every agent I, we fix the policy of all the other agents to be their equilibrium policies, which is U minus I star in here. Then for every agent, if it fixes the policy of the other agents, its equilibrium action or strategy should be the best that it can take while it fixes the policy of other agents. So in a sense, equilibrium captures the fact that everybody is doing what is the best for them given the equilibrium strategies of other agents. And if you want to think about it mathematically, this would translate into this set of coupled optimization problems. If I was just one, if we had just one agent, this inequality would have been an optimization problem. But since we have multiple agents and we need this inequality to hold for every agent, then this will be a set of coupled optimization problems that robots must solve to think about and reason about interactions. And it turns out it's actually particularly challenging to solve this. And what I'm going to do throughout this talk is that I'm going to leverage this strong and powerful framework that game theory provides to talk about how robots can leverage this notion of equilibria to plan across various scales of interactions. At a low level, I will start with interactive motion planning. How can robots generate interaction-aware motion plans? Then I'll go and focus on a higher level decision making at the level of task planning, how to plan for tasks in interactive settings. And then finally, I'll talk about interactions of multi-agent interactions at a network level, at a societal scale, and argue that we should also think about those type of interactions when we are developing these systems. But let's start with interactive motion planning first. How can robots generate motion plans when they are sharing their environments with a number of other agents, and how should they account for the couplings that I just mentioned? So let's look at a simple example. Let's say we have 3 agents. Some of them could be robots, some of them could be humans, and each one of them wants to move to their own goal positions. To plan trajectories in such a setting, robots must find the equilibria in the sense that I mentioned before, and then take the equilibrium actions at every instance of the time. But how should we think about this notion of equilibrium here? So each of these agents are a set of dynamical systems. Their states evolves in time with their actions, and they also have their own cost measures, J1, J2, J3, which, for instance, in the case of a motion planning, could be something like a tracking cost or distance to goal, plus minimizing or penalizing for collisions with other agents. Then in this case, our game, because these agents are dynamical systems, reduces to or becomes an instance of a differential game, which means that the equilibria of the system are now these set of coupled optimization problems that I mentioned before, but they have a dependence over the state of the system and possibly over the horizon of time on which they are making these decisions. So in a sense, this interactive motion planning and this differential game, solving for it, requires solving a set of coupled optimal control problems, which in general could be very challenging and hard to solve for robotic systems, because even solving a single optimal control problem in real time could be challenging. So many of the recent works have looked into different simplifying assumptions or different approximation techniques to hopefully make the computation of these equilibria more tractable and make it more real time. But we started to think, is there any structure that is out there for motion planning that we could possibly leverage to make the computation of these equilibria more tractable and something that robots could do in real time? So after spending some time, we realized that it is the case that under certain cost structures, game-theoretic interactions of the agents will become an instance of a potential differential game. A potential differential game is actually indeed the very general class of potential games, are a class of well-studied class of games in the game theory literature that are shown to have very nice and appealing properties. And one of the properties that was very interesting to us for this class of potential games was that if a game is a potential differential game, then one can show that the equilibria of the game, which are the interactive trajectories, can be found by solving a single optimal control problem. So this means that if one can show that the game is a potential game and then find a potential function, then rather than solving a set of coupled optimal control problems by every robot can simply solve a single optimal control problem, which is in general way easier and more tractable to do in real time. But let me explain a little bit in more detail what is a potential game and what I mean by the term potential function. So let's say we are interested in finding the equilibria of a differential game in which the cost of every agent is a function of the control actions that it would take over a horizon of time. And it is the integral of a running cost, Li, of x of t, u of t, and t. This x of t and u of t can be the state and actions of all the agents, plus some terminal cost, which is Si of x of t. Then it turns out that if we can show that we can decompose the running costs of every agent, Li, and also its terminal cost, Si of x of t, as the sum of functions that are common between all the agents. In the case of the running cost, if we can show that we could write it down as the sum of a potential function P that is common among all the agents, plus a cost term, which is agent specific. It has its dependence on I, Ci, but it is only a function of the state and actions of all the other agents. Then one can show that the equilibria of these potential gain can be found by solving the optimal control problem that is associated with minimizing the potential function of the gain. So the question that we started to think about was, is there a potential function P or a terminal cost term S bar and CISI, which makes motion planning an instance of a potential gain that we can leverage for planning purposes? And we actually proved that interactive motion planning is indeed a potential differential gain when each pair of agents treat each other symmetrically. But what do I mean by pair of agents treating each other symmetrically? Let me again describe it through an example. Let's say we have 3 agents, and then every agent has a running cost that is composed of, for instance, a tracking cost plus a set of coupling costs. For instance, for agent 1, L1 is C1TR, which is the tracking cost of agent 1, plus C12A, which could be the coupling cost that couples agent 1 and 2. For instance, it could be avoiding collisions with agent 1 and 2. And similarly, C13A is for avoiding collisions between agent 1 and 3. And we have the same sort of cost structure for all the other agents. What I mean by agents treating each other symmetrically is the following. Let's say we consider the pair of agents 1 and 2. If the cost term that couples agent 1 and 2, C12 of A, is the same as the coupling cost in the cost function of agent 2, meaning that C12A is equal to C21 of A, then we say that these pair of agents are treating each other symmetrically, which is intuitively, it means that, for instance, agent 1 is penalizing for collisions with agent 2, the same way that agent 2 penalizes for collisions with agent 1. Then if we look at other pairs of agents, and we can say the same thing, that these are treating each other symmetrically, likewise for the other pair of agents, they treat each other symmetrically. If those conditions hold, then one can actually show that the game is a potential differential game. And the potential function of the game is the sum of the tracking costs of all the agents plus the pairwise coupling costs or collision avoidance costs of the agents. And likewise, the terminal cost would be the sum of the terminal tracking costs of the agents. But the interesting thing is that now if we have this structure and if every robot wants to find the equilibria using potential games, then every robot can solve the optimal control that is associated with minimizing this potential function. And that would, for robotic systems, which are normally nonlinear dynamical systems and have non-quadratic cost functions, that would be an instance of a nonlinear optimal control problem. And one can use any algorithm that is really out there for solving or approximating optimal control problems to plan in these settings. For instance, we use iterative LQR for just simply minimizing the potential function of the game. And here is the type of behaviors that would emerge out of potential minimizing. Here is an intersection scenario where the agents start from their start positions and want to move to their goal, but they need to avoid these collisions and sort of yield to each other and coordinate their motion. And they can successfully generate these intuitive behaviors of who yields to who, sort of resolve that conflict. So we were excited by this performance, and then we started to think about what is the computational complexity, or what if our algorithm offers any benefits in computational complexity of the methods. So what we did was, for this intersection scenario, we generated 1,000 random initial conditions, and then solved for interactive trajectories using our method, which we call potential ILQR, and measured the solve time for each one of these initial conditions, and compared it with the state-of-the-art general game solver, which is used for approximating the solution of the games for the same set of initial conditions. And we actually noticed that on average, our method would be 6 times faster than the state-of-the-art game solvers. We did some mathematical analysis of computational complexity, and it turns out that by using this reduction to potential games, our method is more scalable in the sense that its computational complexity is constant in the number of agents, whereas the game solvers are cubic in the number of agents in the environment. So we even moved one step further, and we thought, can we really achieve real-time planning in a set of dynamical systems that are more of high-dimensional dynamical systems? And we considered collision avoidance settings for 2 quads. The 2 quad rotors start from their start positions, move to their goal. And you can see by running this potential minimizer in a receding horizon fashion, they manage to avoid collisions with each other, and they change altitude for avoiding collisions with each other. Here's another video of quads being in this diagonal shape, moving in 3D, and again, manage to coordinate their actions in such a way to avoid collisions. So we were excited by this result, but then we started to think that so far everything has been deterministic. We didn't really think of anything uncertain in the system. We didn't think of any notion of noise in the system. So the next question that we started to think about is, how can we generate interactive motion plans when the system has some noise in it? Or in general, when there's some notion of uncertainty in the system? Naturally, the way to think about it is to either extend the deterministic setting or this notion of equilibria to the setting where agents are minimizing the expected value of their cost function. Or the other option would be to think about a worst case analysis where every agent is minimizing the worst case cost measure. But in the case of using expected value minimization, that may not be a really safe thing to do in the presence of uncertainties. For instance, if you have Gaussian noise in the system. And then if you want to do a worst case analysis, that may also be too conservative. Again, if you have a noise that has like an unbounded support, something like a Gaussian noise. So we start to think about what is the right way of agents making decisions under uncertainties, or let's say under noise, which is a middle ground between that worst case analysis and this expected value minimization. And when looking into the literature of how humans account for uncertainties in decision making and all that, we decided that maybe it makes sense to actually model decision making under noise by capturing the notion of risk that agents maintain on the actions that they will take. So the assumption here was, if there is noise in the system or some source of uncertainty, maybe it makes sense that we model every agent as an agent that is minimizing the risk that is associated with its cost measure. And then to model the outcome of the interaction, then we probably want to model the interaction of risk-aware agents as a risk-aware dynamic game. But first, how should we quantify that? And once we have a mathematical characterization of it, how should we solve for the equilibria of such games? So for capturing the notion of risk in the decision-making process, we chose the entropic risk measure. We assume that every agent is minimizing, rather than minimizing the expected value of its cost function, we assume that every agent is minimizing the entropic risk on its cost function, which is the log of the expected value of the exponential of the agent's cost function. And every agent has a parameter theta I, which is sort of like the risk tolerance of the agent, in the sense that if every agent, let's say, has one parameter theta of I, if theta is equal to 0, that means that just the entropic risk simply reverts to the risk neutral case. And when theta is greater than 0, it means that agents are risk averse. They don't want to have risky behaviors. And when theta is less than 0, agents are risk seeking, meaning that they are actually exploring or are interested in experiencing more risk. So if we model it through this framework of entropic risk, the question for us was, how should we think about finding Nash equilibrium policies of such a risk-aware dynamic game? In a sense, how should we find the strategies gamma I for every agent such that the coupled optimization problems that I mentioned before, this time holds for the risk measures that every agent maintains on its cost function? So we're looking for ways to find this, hopefully in a tractable way so that it can be run in real time. And then to do that, inspired by the success of iterative methods, such as iterative LQR methods in robotics, we used a previous result from the risk-sensitive controls literature, which was the following: that if the system dynamics is a linear dynamics, by system dynamics, I mean the state of all the agents evolves linear in time. Here, x of t is the vector of state of all the agents. If these dynamics are linear and they're subject to a Gaussian noise, and also the cost measure of every agent is a convex quadratic function of the state and actions of the agents, then it can be shown that the Nash equilibrium policies of this entropic risk, this game with entropic risk measures, can indeed be found in closed form solutions through a set of equations which are indeed the extension of Riccati equations to the multi-agent setting. I haven't included the set of equations because there are just so many of them, but the idea behind it is very simple. It's just the extension of Riccati equations to the multi-agent settings, which results in solving a set of matrix equalities. And then there's also a slight modification of them to account for this notion of risk awareness, and theta I actually appears in the set of equations too. So by having this result that in this class of games, which are called LEQ games, the equilibria can be found in closed form. Then for general nonlinear systems, we use an iterative algorithm, which basically we linearize the dynamics, had a quadratic approximation of the costs. For the resulting LEQ game, we found a closed form solution. We used the closed form solutions to find Nash equilibrium policies, and then repeated this process until convergence, very much similar to this notion of iterative algorithms that are normally used in robotics. Then, by leveraging this type of iterative algorithm, we actually recovered the behaviors that we intuitively expect out of the system. So here we are considering, again, two scenarios, an intersection scenario and the freeway merging scenario. In this case, we are modeling the behaviors and we're showing the behaviors that emerge out of risk-aware interactions when the green agent is more risk-averse than the red agent. And we observe that in most of the simulations, actually, it's actually the case, the green agent yields to the red agent, which is what you may intuitively expect when one of them is more risk-averse. But then we start to think, let's see how the behavior or how the interaction of the agents varies as you change the risk sensitivity or risk awareness parameters for the two agents. So for instance, consider, again, this freeway merging scenario. What we did was we measured the frequency of the red agent yielding to the green agent for 10 random initial conditions. And then we computed this for different pairs of theta 1 and theta 2. And for the same set of initial conditions and same pairs of theta 1 and theta 2, we measured the minimum distance between the two agents. And we actually saw that the type of behaviors are, again, very intuitive in the sense that they follow our intuition. First, if you look at the minimum distance between the two agents, as you get further from this dashed line, meaning that you move on this plot and in the direction that is perpendicular to this dashed line, the minimum distance between the two agents increases, which means that as the relative risk sensitivity of the agents increases, the minimum distance between the two of them increases. which means that if one of them is way more to the risk averse than the other agent, then of course it want to maintain a distance with the other agent. Or when you look at the frequency of one agent yielding to the other, when both of them have the same risk sensitivity or risk awareness parameter theta I, when it is theta 1 is equal to theta 2, the frequency of yielding is very close to 50%. 50% of the time one yields to the other, which again makes sense if they account for risks equally. Another interesting observation that we made out of looking at this qualitative behavior of the agents as a function of their risk awareness is that some of these behaviors are not explainable without considering the interactions. For instance, imagine you're a risk-averse driver, but when you are driving around another driver who's too risk-averse, you are sort of incentivized to exhibit a maneuver such as a lane change, which may in itself be interpreted as a risky behavior. But that doesn't mean that you are a risky driver. It just means that because you've been driving around someone who's too risk averse, you're just exhibiting a maneuver which may in itself be interpreted as a risky maneuver. So those were also interesting to see in this type of experiments, that those qualitative behaviors that can be explained by looking at interactions of risk-aware agents. But the overall message and the takeaway message that we got from this was that in order to generate interactive motion plans in each one of these cases, we really need to account for the coupling between agents' trajectories. And the challenge and question that we're still working on it is how should robots plan for these couplings in real time? How can we find the equilibria of these games in a tractable way? But these motion plans are not really the only level at which robots should make decisions and plan. What I want to do next is that I want to talk about decision-making at a higher level, moving beyond motion plans at a higher level, let's say task planning, something like role assignment, who is going to do what, or deciding on the population of robots who should take a certain action. How should robots plan for these higher level decisions when they are interacting with the other agents? And I'm going to explain these notions through, again, some running examples. And I'm going to start with role assignment in multi-agent interactions. So consider a simple example that two robots want to carry a rod, an object, in a room, and they are sharing that room with, let's say, two humans. Can, for instance, assume that the two humans want to move their own goal positions. They have their own trajectories, or they want to plan their own trajectories. And also the two robots want to move the object transported to its goal positions. And at the same time, they want to make sure that they don't avoid collisions with the humans in the environment. How should robots plan for these actions? If you think about it, how humans do collaborative transport in such settings, let's say two humans that are carrying a heavy table together, what normally happens is that at every instance of a time, one of the humans is leading the transport and the other human is normally following the leader and just changing the orientation of the table to avoid collisions. Sort of inspired by that, we started to think, can robots decide on these high-level decisions of roles of who is going to be the leader at every instance of a time and who is going to be a follower, dynamically decide on that role assignment so that they succeed in these type of interactions. And the assumption that we made here was that the leader is, both of the leader and follower are responsible for avoiding collisions, but the leader is spending more control effort and the follower is just trying to minimize its control effort. So the follower copies the leader, but with way control effort. So we start to think, is it important to decide on how this role assignment should be done to succeed in these type of interactions? So we first started with trying random role assignment or leader, follower to see how the system would perform. Since this is a very recent study, the simulations are still preliminary, but I think they still convey the message. we found that in all these cases, we have suboptimal performance due to inappropriate selection of the roles of the robots. So on the left, you can see, you even don't see the robots anymore, because by assigning them to both of them be followers, the mission basically fails and you don't see the robots in the scene anymore. If you let both of the robots be leaders, we have excessive control efforts, so we have suboptimal performance. And if we have random assignments, the rod actually collides with humans, which is what you can see now on the right, that one of the humans actually collided with the robots. So the blue and yellow dots were representing humans. So this shows that in order to be successful in these tasks, robots need to make these higher level decisions of who is going to be the leader, who is going to be the follower in real time. So we started to model that again through this game theoretical framework that I mentioned at the beginning. And we formulated this role assignment as an instance of a dynamic game. But that dynamic game turns out to be a very complicated game, because there is, at the low level, still that motion planning thing that I mentioned at the beginning happens, but there is this additional layer of who is going to do what as a discrete choices of what role each one of them should take. So we used some of the tools from empirical game theoretic analysis to analyze these games, to find the equilibrium of this sort of like hybrid game. And then once we find that, every robot can take the equilibrium strategy at every instance of the time and to succeed in a task. But let me explain what I mean by the second step, which is using empirical game theoretic analysis. So empirical game theoretic analysis is a tool that has been developed by computational economics computational economics for analyzing the games that are really complex and hard to model. And the way that we sort of started thinking about this problem is that we formulated role assignment as some sort of a meta game. What do I mean by that? So let's say being a robot, being a leader can be translated into a control policy that is associated with being the leader. And being the follower will result in another control policy, a set of policy that is associated with being the follower. Then what we do is that we construct a meta game, the payoff table of the robot teams, as a function of these role assignments. And what we do is that, for instance, we try to fill up the entries of this payoff table. We want to see what is the cost measure of the robot teams when both of them are leaders. This will require us to solve, as I said, the lower level decision-making problem. But to sort of approximate that, we generate a set of samples that will result from this role assignment, and we compute the payoff that is associated with this role composition. And then we can similarly fill up this table of what is the payoff function if each one of these role assignments were chosen by the robot, and just find the equilibrium strategy out of these role assignments. And then robots can dynamically do that. And here you can see that if they do that, we allow frequent role switches by running this empirical game theoretic analysis in a receding horizon fashion. Robots can successfully change their roles to avoid collisions. The robot with the large aligned segment is the leader. You can see they just constantly switching who is going to be the leader. And then they manage to successfully complete the task and without colliding with humans. So this was just one instance of task planning, in a sense of who is going to do what in order for the robot team to succeed. But those are not the only ways, the only high-level decisions that robots need to make. One other question, or one other higher level task planning, is predicting the population of agents who should exhibit certain maneuver or make a certain choice. For example, consider again a driving setting. You want to predict how many of the cars should take a certain lane. So in a sense, you want to predict and plan for the population of agents who should take a certain lane. So that is another more of a higher level of decision making, again, in these multi-agent interactions. So for instance, consider a freeway link that is bifurcated into two exit lanes. Let's for now just focus on the case where all cars are human driven. Let's say if we can understand those and then think about how should we think about this higher level decision-making problem when there are robots in the environment too. So let's say, for instance, that the demand of cars for exit P is higher than the demand of cars for exit Q. If you think about it, normally what happens is in practice is that not all cars would remain on lane 1. What happens is that in practice, some form of a bypassing maneuver occurs where basically some of the cars, the blue cars in this case, take the less occupied lane, lane 2, and exhibit this bypassing maneuver and then take exit P at the very end. They change their lanes. So we started to think, can we model lane choices of the vehicles in the sense of how many of the vehicles would make a particular lane choice, again, as a meta game, and use that for prediction and planning. So to verify that sort of conjecture, we first focused on the case where all cars are human driven and to see if we can actually predict humans' lane choices as a meta game and then leverage that for robot planning. So we construct our meta game in the following way. Let's consider cars that take exit P. Let the population of cars that take exit P be Fs of P, which we call steadfast cars that take exit P. And we assume that all of those steadfast cars experience the same cost function, Js of P. And then we also have a population of cars that take exit P through this bypassing maneuver, through this lane change behavior. Intuitively, and again, we're assuming that these bypassing cars will experience the same cost function. So intuitively, if you think about it, when you're watching a set of human agents exhibiting these type of behaviors, if there is a non-zero flow of steadfast cars or non-zero population of steadfast cars, this means that these cars did not have any incentive for taking the bypassing maneuver, which means that for them, the cost of being steadfast was lower than the cost of bypassing. And if there is a non-zero flow of bypassing cars, then it means that the cost of a bypassing maneuver for these type of cars was less than the cost of being steadfast. In a sense, they didn't have any incentive to act steadfastly. And if you think about those conditions, it turns out that these conditions about the population of the agents can indeed, again, be cast as a Nash equilibrium or some form of equilibrium for the flow vector or the population of agents exhibiting each one of these maneuvers. So we constructed this metagame and we saw, does this metagame, and we modeled this JS and JB, and we asked the question of, does this metagame explain the lane choice of vehicles when they're actually driving, let's say, in a freeway? And to do that, we use Sumo simulations. Sumo is an open source traffic simulator, which models vehicles' behavior at a micro level. It uses car following models. And what we did was, again, we considered this freeway lane. We fixed the number of cars and changed the fraction of cars that want to move to exit P. So the x-axis is the fraction of cars that want to take exit P. When it is 0, it means that all cars want to take exit Q. When it is 1, it means that all cars want to take exit P. And for each one of these fractions of demand, we measured the population of cars that exhibit this bypassing maneuver for every fraction of the demand. The orange curve is what the simulation shows us, and the blue curve is what the metagame predicts for us. And as you can see, the predictions of these metagames is very close to what you could get from a micro simulator such as Sumo, which is using car following models, which was pretty impressive. And also it is intuitive what the model is predicting. You can see that the bypassing cars are, the population of bypassing cars starts to become non-zero as soon as the fraction of the demand that wants to take exit P goes beyond 0.5. Because if less than half of the demand wants to take exit P, it doesn't make any sense actually for the cars that want to take exit P to do a bypassing maneuver, because the lanes that go to exit Q would actually be more occupied. So having that verified, that this metric games can predict humans' lane choices, the natural question was, okay, what if we have a number of autonomous cars, all our cars are autonomous, how many of them should do this bypassing maneuver, how many of them should act steadfastly? And we can even ask some other questions of how should the autonomous cars choose their lanes in such a way that, let's say, the overall performance of the system is minimized or the overall cost of the agents is minimized. So what we did was we considered the overall cost of the system, which is the sum of the costs that all agents would experience. And we found the amount of bypassing for autonomous cars that want to take exit P is required for minimizing the cost function of the agents when all cars are autonomous. We may at the beginning think that we need no bypassing for minimizing the congestion or the total cost of all agents, but it actually turns out that we may need a little bit of bypassing to actually optimize the performance. So in a sense, that optimal form of bypassing is required for maintaining the trade-off between the improvements in the performance that the bypassing cars get, whereas the increase in cost that bypassing cars will create for the steadfast cars. So the orange curve in this case is the number of bypassing cars that you would get when all cars select their lanes selfishly. You let autonomous cars just select their lanes selfishly. And the blue curve is the amount of bypassing of autonomous cars that you require for minimizing the overall cost of the system. And you can see that there is, when you let them all be selfish, then there is too much bypassing occurring, which reduces the system efficiency. But there is a little bit of bypassing that you may require for minimizing the overall cost. So this gives us a way to actually plan for the population of robots who should do this bypassing maneuver. And now we can even take it a step further and think about a mixed autonomy setting where some of the cars are human-driven, some of the cars are autonomous, and then dependent on the fraction of the cars that are autonomous, think of what population of autonomous cars should do this type of bypassing maneuver and change their lane. But I'm not going through the details of it because the type of behaviors are very much dependent on how many of the cars are autonomous, how many of them want to take each one of the exits. But the point here was that we want to make sure that robots are capable of predicting and planning for agents' higher level decisions and higher level choices to actually succeed in interactions. But this, again, as I said, I want to take this a little bit further and think about decisions at a higher level scale of interactions in the remaining time to sort of briefly talk about those two, because these type of lane choices and decisions are not the ultimate level of decision making. These multi-agent interactions will have societal scale implications and network level impacts too that we must be aware of. And I really want to make sure that I talk about those very briefly in the remaining time. So I'm going to focus on the societal scale interactions. When you have a large number of robots, a large number of humans interacting with each other, what happens in the system? And probably the most foreseeable form of these interactions is when you have a fleet of autonomous cars, you have a large number of autonomous cars being deployed on the roads. And then the question is, if you let all these autonomous cars interact with human-driven cars, how would the behavior of the system look like? For instance, are we guaranteed that the mobility will increase by simply replacing human-driven cars by autonomous cars? What are the type of behaviors that we could expect? You may be thinking that when it comes to such system level impacts, how are autonomous cars different from human-driven cars? And one particular difference that I want to focus on, just as an example of how things could be different, is the fact that autonomous cars can increase road capacities by using their communication technologies and forming platoons of vehicles. And this seems great because we think by replacing human-driven cars by autonomous cars that can form these platoons of cars, effectively we are increasing road capacities, which is something like increasing the number of lanes in the roads. So at the first glance, it may seem like increasing road capacities will improve mobility. But there is something in transportation literature called Brace's paradox, which indicates that sometimes constructing more roads or increasing road capacities, even in networks of only human-driven cars, may indeed just worsen traffic congestion. And this has been observed throughout the world in different times. Sometimes governments had to deconstruct the bridges that they had constructed because the addition of that road segment or the addition of certain lanes really worsen the overall situation. So if we are thinking about these type of counterintuitive behaviors emerge when humans are interacting with each other, how are we guaranteed that when autonomous cars increase road capacities and they interact with human-driven cars, something similar to the braces paradox would not occur? Are we guaranteed for that? So since we don't have too many autonomous cars on the roads now, we started to study this problem theoretically through the framework of routing games, which is basically the game theory literature when there is a network of decision-making on a network involved, where we have the network has a set of nodes, links, and a set of origin-destination pairs. And then in a mixed autonomy setting, which is when both human-driven and autonomous cars are present, for every origin-destination pair, we assume that we have a fixed demand of car and an alpha fraction of the cars are autonomous along that OD pair. And then there are sort of possible routes for every origin-destination pair. And then the question that we were interested in is, if we let these systems interact with each other, how are the autonomous cars and human-driven cars routed throughout the network? So if we consider let's say a route P, the flow along the route P is composed of the population of human-driven cars, which is denoted by f of h here, and the flow of autonomous cars, which is denoted by the f of a here. So we theoretically studied this problem of, are we guaranteed that when human-driven cars are replaced by autonomous cars that maintain these platoons, mobility will improve? We characterize the conditions under which such a guarantee exists. I'm not going to discuss those conditions, but then we actually found some counterexamples in which one can see that using autonomy and autonomy deployment may actually increase the societal cost or the overall congestion in the system. So consider a simple example. So the cars want to move from origin O to the destination D, and a fraction of them are autonomous. For every fraction of these cars that are autonomous, we measure the maximum and minimum overall cost or social delay of the system at equilibrium. And here is what the plot looks like. If you look at the overall delay of the system at equilibrium as a function of the autonomy fraction, it is not a non-increasing function. The maximum overall delay increases up to some point and then decreases, whereas the minimum delay decreases and then increases. And surprisingly, when alpha is equal to 1, which means that all cars are autonomous, the overall delay is actually higher than when alpha is equal to 0, which is when all cars are human-driven. So if you just replace human-driven cars by autonomous cars and let them interact with each other, we may actually end up with a situation that is worse than what we currently have. And something similar to Brace's paradox may happen this time because of autonomy deployment. So the point of these counterexample and
Negar, sorry.
Yes.
No,
yes.
I just cannot stay silent.
Sure.
What are assumptions? I mean, this seems to be a very poor choice of the autonomy design.
So the assumption that that's exactly what I wanted to talk about next, that if you just let your autonomous cars just select their best possible routes, the same way that human-driven cars choose their routes, then that is what would happen.
But that's with human-driven cars, right? So it's not that autonomous cars are making things any worse. So, okay, fine. Exactly. I look forward to the next step, but
yeah, sure.
You can make a statement as autonomy deployment, blah, blah, as a general statement, because people then misunderstand these things. So
yeah, that's a good point.
Let's move on. Okay.
Yeah. Thanks for that, friends. Thanks for the feedback. But the point that I want to make here is that it is exactly like what you mentioned, that it is routing decisions of autonomous cars can influence humans' choices, humans' routing decisions. And that can result on undesirable global properties such as congestion. And that's the point of, if we are not thinking about how autonomous cars should be selecting the routes, then the way that human-driven cars would respond to them may actually worsen the congestion. So we started to think theoretically, how can we bound the performance degradation that will result from these replacement of human-driven cars by autonomous cars that I'm not going to discuss. But the question is, if such a behavior can happen because of the interaction between autonomous cars and human-driven cars, does it even make sense to let autonomous cars route themselves through their best possible route? doesn't it make sense to think of routing autonomous cars in an altruistic way, such that when human-driven cars respond to the route choice of autonomous cars, the overall system efficiency actually improves, and we avoid something like a Brace's paradox that I mentioned in the beginning. So the point is, when we think about these systems and let's say using autonomous cars, we also need to plan for not only how they should choose their speed or lane choice, but also how they should pick the route, such that when human-driven cars interact with them and respond to those route choices, the overall performance of the system is improved. And this is something very relevant to Stackelberg routing in the game theory literature that we've been studying for this class of mixed autonomy routing games. So yes, it is not that autonomous cars inherently are worsening the things. It's the fact that how human-driven cars are responding to autonomous cars, route choices, that is worsening the performance of the system. And that
not only that, but also the design of the routing for the autonomous systems, right? So
yeah. I mean, but you know, the situation actually becomes more complicated when there are multiple OD pairs. So if, for instance, you have, I actually didn't include that example. I think I have it in one of the slides. If you have autonomous cars along only one of the OD pairs and let them, again, increase road capacities through this platooning, then human-driven cars from other OD pairs may be incentivized to take the route that autonomous cars are taking. And then that would, again, worsen the overall situation. So the fact is, human-driven cars are acting selfishly. And then the point that you're making regarding the proper design of the autonomous cars would be, for instance, not allowing autonomous cars to form platoons in such network geometries to avoid such undesirable outcomes. So there is, of course, an element of what is the proper design of the autonomous cars to avoid this complex behaviors. But the point is, we need to account for the fact that human-driven cars would be selfish and then respond and take the best possible best possible decision for them. So that's actually what I'm hoping that we can get, that we needed a very proper design of the autonomous cars to achieve mobility improvements on the network. So I'm hoping that you're convinced that robots should account for decisions and coupling across different scales of interactions, from motion plans to high-level decisions to societal scale interactions. But this is just the start of the journey, and there are many more domains and applications to think about. Throughout this talk, I basically assume that I know the cost measure of all the agents, but you may all, of course, question that. How do we know the cost function of every agent, especially if a robot is interacting with humans? How do we know the cost function of the humans? And then we can use some ideas, for instance, from inverse optimal control or inverse reinforcement learning to actually learn agents' cost functions from their demonstrations. But then when it comes to interactions, of course, we must agent cost functions from their interactions, sort of extend the setting of single agent reinforcement learning to the multi-agent setting. And finally, there are many forms of interactions that humans are really good at that robots are not capable of doing now. Humans are very scalable in their interactions. They can share roads with hundreds of pedestrians and then reason about those interactions. They are extremely good and well in collaborating with teammates in particularly challenging tasks. And humans are even really good at collaborating with each other within a team and then competing with another team of agents. That robots are now just still really good at. So it's really thinking about all these forms of interactions that hopefully robots could achieve one day. But with that, I would like to, I know it's already 10 a.m. Central Time. So with that, I would like to thank all my collaborators and students, and thank you all for your attention. And I'd be happy to answer questions and discuss the talk further. Thank you, everyone.
Thank you, Negar, for the talk. Is there any question from the audience? If yes, please unmute yourself and go ahead. Oh, Emilio, go ahead.
If I may, Andrea, thank you, Negar. Yeah, very, very interesting, a lot of things. So one of the assumptions, I mean, when for example, you had the interaction with the red and the green car, right? So I'm just thinking of an example. You assume that you know the utility function for the other guy.
Mm-hmm.
Okay, so what if that is not true in the sense that, you know, different drivers may have different costs or utilities or payoffs, right?
Right, exactly.
So what would you do in that case?
That's a great question, and that is because that is exactly why I think without having the mechanism to infer and estimate agents' cost functions in real time, it's not really, it may not be feasible to do this type of planning, especially when you are working with a human agent around you. So the way that we've been thinking about this is there is a lot of data out there that one can use for learning agents' cost functions, maybe as a good prior of agents' utility function. But then in the next step, we actually need some form of a real-time inference and estimation of how to sort of modify that prior to actually model the behavior of the agent and adapt to the new form of driver that you may be interacting with. And one particular idea that, for instance, we've been thinking about is that if we have a good prior and we can sort of characterize the risk behavior of the other driver through some simple parameters, such as like theta parameter that I showed in this, it would actually probably make it easier to infer an estimate of the theta of the other agent based on the ongoing trajectories of it in real time, as opposed to learning the entire cost function in real time. So we are assuming that we have a good prior of agents' cost functions. And then there is, of course, this new element or new layer of we should be adapting ourselves in real time to different types of users and agents that we may be interacting with.
Yeah, thank you. Now, let me get back to the, to the autonomy can make things worse, right? So
sure.
I think that, my reaction was due to the fact that, in one slide you say, autonomy can make things worse. And then the next slide you have autonomy can make things better, right? So it's clear that we have examples of both. Right? Now, and, I'm a little bit sensitive about this maybe for obvious reasons, but,
I knew that you would ask questions about that.
So, so in a sense here, what we want to do is do good science and avoid clickbait, right? So, kind of like, like a, kind of like, things that a reporter would write just to get more reads on his or her article, right? So at the end, okay, so what we want to, like autonomy is something that we are, people are working on it because there is an aspiration that will make things better, right? So now this aspiration may prove to be untrue, right? So, but then what I would say is, if you really want to say that autonomy will make things worse, is that by proving that there is absolutely no design for the autonomy that will improve it, right? So that for anything you do, things will be worse. Okay, so then I will accept the title that says autonomy. Right? But if you have at least one example, right, that makes things better, then you should write it. And then, then autonomy can improve things. Okay.
Yeah.
Otherwise,
that's a good point. Yeah.
That's kind of like what is, is the, yeah, okay. So I can write an article by saying, I designed a very poorly designed autonomous car, and then I do experiments, and this poorly designed autonomous car kills a lot of people, right? So then people say, oh, autonomy will kill a lot of people. No, that's poorly designed things kill people, right? But so the interesting article is the one about,
I see your point. Yeah. Yeah, that's a good point. But the point that I'm really trying to convey here is exactly what you're mentioning, that I feel like, especially for instance, when you're in Bay Area, everybody is by default assuming that as soon as autonomous cars are on the road, things will get better. And that is not true. You need to think about, you need to plan for things. You need to come up with the right control algorithms to actually ensure that, because
but then you should write, like a poorly designed autonomy can make things worse.
Right.
Yeah, I have nothing against
so
that.
I have some other example that maybe I can try to actually find it. I think it's part of my slides, which is, as I said, with this autonomy deployment allowing this specific OD pair, that actually again goes back to autonomy design, which is the fact that if we only have autonomous cars along one OD pair, and then the human-driven, all cars along other OD pairs are human-driven, then the overall system performance may actually get worse again. Let me actually try to find that.
It reminds me a little bit of like a Bryce paradox, right? So this is a version of paradox. Yeah.
Yeah. So then the way that you could think about it is, if, for instance, one neighborhood is the richest one to be the first to start using autonomous
but the fact that you have Bryce paradox doesn't mean that you don't build new roads or new bridges, right? So it means that you're careful when you build a new bridge, right? Or
right, exactly.
Right? So,
yeah, I completely understand your point, and I'm not saying that things are going to be absolutely terrible. It's just a matter of really accounting for those interactions when there are both human-driven cars and autonomous cars. And then it actually turns out that those class of routing games are much more complex to analyze than routing games on just human-driven cars, because they don't have the nice properties of only routing games with human-driven cars. And so that requires a little bit of attention on the design of those control systems.
Right, but you had the advantage that with autonomous cars, it's easier to pose something, that is closer to some social optimum.
Right.
Then it remains to be seen if the passengers will get on your car versus getting on a competitor's car that chases their optimum rather than the social optimum. But anyway, so this
then it brings this question of, at the end of the day, the autonomous cars, there would be some humans sitting there, and then up to what level can you assume that you can control your autonomous cars altruistically, in the sense of like minimizing the overall performance?
Can't you claim that that's the problem is made no worse than having humans that do not typically behave altruistically, right?
Yeah.
Anyway, but
so
I don't want to steal all the time.
No, I mean, that's a very interesting thing, because I think about it a lot, and I really want people to think about it, is, for instance, do autonomous cars provide some form of like an incentive or mechanism for human travelers to act more altruistically? Let's say if we tell them that, hey, you're not driving your car, so are you willing to take a route which is like 10 minutes longer than your usual route, but this time you're not driving your car, so that's your choice. Do you want to be altruistic a little bit once you're taking autonomous cars? And then sort of plan for these autonomous cars routing in such a way that the efficiency of the system is increased, or like changing the the time that people travel by using autonomous cars as like an incentive mechanism for them to change their behavior, because traffic congestion in nature really happens because of humans' choices and the way that humans behave, right?
Right. So that's why, of course, you can make the autonomy as bad as humans, right?
Yeah, of course, especially if they're designed with humans. You need to be careful.
Probably you have a little bit more tuning parameters, right? So that you can design something that is improving things at least a little bit. Anyway, but let's see if there are any other questions.
Actually, before that, I want to show this example, which I think it's actually another interesting example. So this is just another very simple network. We have A, B, and C. Cars want to move from A to B, from A to C, and B to C. And we only have autonomous cars when they want to move from A to B. And then we're computing the social delay at equilibrium as a function of autonomy fraction along AB. So what happens is that when you replace some of the human-driven cars along AB by autonomous cars, the cars that took the route AC are now incentivized to take the route ABC.
Right.
And that would increase.
Don't get me wrong. I totally believe that this is true, right?
Yeah. No, I just wanted to point out
that anybody would ever deploy autonomous cars this way. Right.
Yeah, exactly. So I just want to know, this is just an exciting observation that I've had, that here again, the social delay increases.
Again, but for me, it's not very surprising, right? Because, I can design an artificial system to perform as bad as I want. It doesn't mean that I should do it, right? I can make an autonomous car much more dangerous than a human-driven car. Yes, of course I can do it. Right. But would I? No. Right. So
yeah, and I think that's our job as controls people, to just be aware of all these aspects of the designs that we make and control decisions that we need to put in place.
But then our job is not to scare people with those titles.
Yeah, I should better move from this slide. I know you don't like the title.
Right. Anyone is brave enough to ask another question after this discussion? If yes, you can unmute yourself and simply ask the question.
Hi everyone, I can give it a go.
Sure, Dario, go ahead.
Hi Negar, thanks for the talk. It was quite interesting. I had a question regarding the first part of the talk when you look at essentially trying to avoid intersection between robots. So you essentially look at the problem, you formulate it in the language of Nash equilibrium, right? And I was wondering if there is any sort of underlying assumptions that sort of support this modeling of the emergent behavior, meaning why should we be choosing a Nash equilibrium? I mean, this is something that people don't believe even when we have rational agents. So why should I put this sort of extra modeling on top of an instance where there are robots mixed with humans, mixed with a number of other parties?
That's actually a great question. So you may actually think about it in different ways. One is exactly what you said, that how good are these models, given that we know that humans are boundedly rational, although they may not have like infinite computational power? How are we guaranteed that humans are actually reaching a notion of equilibrium? And first, I want to say that these type of behaviors, these type of game theoretic plannings, at least seem to generate these intuitive behaviors that we normally expect to happen when humans are interacting with each other. But then the question is, can we actually verify that that is exactly the same way that humans normally make decisions? And I think that can be thought of in different ways. One is, can you find a utility function for humans that rationalize the human's behavior as an equilibrium seeking strategy? Is this something you could do? Which is actually some recent work that we've been doing, which is how good is this assumption? And then second, how can we account for humans' noisy decision-making on top of this modeling framework, where basically we assume that everybody is minimizing their utility? So can we modify this model so that we can have like a noisy human decision-making, or add noise to the human's decision-making process, and then a robot plan based off of that? And that actually turns out to be another thing that one could try. But the third thing that I want to mention, which that is actually something I've been thinking about in these past 2 weeks, so I still have to verify this conjecture. But to me, it seems like maybe the class of games that the agents are solving when, for instance, they're generating motion plans, if, for instance, it is a class of simpler games, something like potential games that I talked about at the beginning, those class of games are much easier to solve and to converge to an equilibrium in them. And they are way better than the class of general games where basically you don't even know whether an equilibrium exists, how many of them exist, and whether the agents will learn to find that. So maybe it's actually the case that because these games are a class of simpler games, they could be something that humans can manage well, and they can explain the human's behavior. But if you're looking for me to just say, I'm 100% sure that's like the best way of modeling humans' decision-making and planning in these interactive settings, I cannot really claim that. But just it turns out that based on what we're seeing or the alternatives that we have, if we want to go beyond predicting the other agent's behavior and just plan to react to that, and if you want to take into account the coupling between the agents, the fact that if I do this, here is what the agents would do to have them simultaneously, this game theoretical planning seems to be working well.
Okay, thank you.
Thank you for the great question.
All right, we went a bit over time, but if there's a final, maybe quick question, we can have it.
I'd be happy to hear questions.
Right, doesn't seem so. Thank you, Negar, for the talk. wishing you good luck for the next steps.
Thank you. Thanks everyone for listening to my talk. I really enjoyed it, and thanks for your thoughts and opinions on this.
Thank you very much.
Thank you, Negar.
Thank you.
See you
Have a
everyone
good day,
next
Thank
everyone.
you. Bye-bye.
Bye-bye.
Bye.